Okay, so we now know the notation for basic hypergeometric series, and we will now prove the important Q series identity or basic hypergeometric series identity called Q binomial theorem. This is simple but very useful, and many Q series identities or hypergeometric series identities can be derived from this. So this is 1 phi 0 A nothing Q Z. This means the same as this. So this is equal to A Z Q infinity Z Q infinity. Okay. In other words, 1 phi 0 can always be written as a product, 1 phi 0, because this is general form, A, Q, Z, they are all in general form. 1 phi 0 is always expressible as a product. Proof. There is a combinatorial proof of this, but I'm going to prove this using just Q series, just to show you how it works how it is done in Q series. We will find a recurrence relation for this. So let's say H sub A Z equals the series, this series. So by definition, this is equal to A. So this is basically the left-hand side. So the identity says this is equal to this, basically. Now we will make some recurrence relation. So consider first consider HAZ minus HAQZ. We will consider the difference of these two. And summation n from when n equals 0, they both 1, so we can consider n from 1. Then QQn AQn minus AQQn Zn. All right? I just expressed that using this. And now what? We can factor. So they have common factors. A, Q, n minus 1. Then this part, it begins with 1 minus A. So we have 1 minus A for this. And this has the last term is missing here. So basically the first factor is missing and the last factor is missing. So minus, the last factor is 1 minus Q, AQ to the n, Z to the n. Okay? We can cancel this and this. And factor minus A out, then minus A from 1, Q, So what is this? So we cancel this, minus A, 1 minus Q to the n. All right? Then this will cancel one of the factors here, right? You can cancel this with the last term over here, last factor of this. That gives us 1 minus n. Do you see? Because this has 1 minus Q squared, 1 minus Q to the n. The last factor will be cancelled with that thing. And we factor Z out, AZ, and then it begins with 0 now. We replace n by n plus 1, then z to the n, which is minus a z h a. Oh, okay, I forgot to have this parenthesis. A q. Okay. So we obtained one thing. This is equal to this. And similarly, if you consider a QAZ minus, now you multiply Q there, QAZQ. Then, by the same idea, you obtained something like this. 1 minus a z h a q z. You apply the same idea. Oh, yeah, actually, I forgot. From this, okay, let's write this. This part is equal to this. We can simplify this to obtain HAQZ, because they have the same thing, term, equals 1 minus AZ, AZ, okay? So this part is equal to 1 minus a z, 1 minus a z, h a of z. So now we can simplify this thing. This equals this, because they have the same factor here and here. So finally, we get HAZ equals 1 minus AZ. This is a computation, ZQ. We obtained a recurrence relation, some kind of recurrence relation or functional equation like this, by considering the two difference of this and this. Okay? Now you apply you keep applying this. You apply this again, then you get 1 minus AZ, 1 minus Z, 1 minus AQZ, 1 minus QZ, ZQ squared, right? So dot dot dot. Then at the end, if you apply this n times, then you get AZ Q sub n, Z Q sub n, H A Z Q to the n. If you apply this like n times. If you apply this infinitely many times, n in other words, n goes to infinity, then you get n approaches. What happens if you have this? So basically here we have z times q to the like very large factor, and that is 0. This is oh no, not 0. This goes to 1 because this thing is 1 plus something, 1 plus something times z raised to 1 plus something times z raised to 2, but z has infinite power of q, so it's going to be 0. Except the first term, they all become 0. So it's 1. So that's it. So n approaches, you just make this limit n approaches infinity, then you get this thing, a z q infinity, and this thing z q infinity, and this thing goes to 1. So that's the right-hand side. This is the proof, one proof using Q series. So in Q series, we prove identities using this kind of idea. Find the functional equation and try to iterate the equation that you found. Right? And it is also possible to prove this using combinatorics, using partitions. I wrote that down in the lecture notes, so if you are interested, you can read the lecture notes. Any question? So a binomial theorem is like this. Summation n choose I x to the I, but this doesn't look like this. But we will see that there is several consequences of this theorem, and one of them is Q version of this. You will see that. So corollaries. So if A equals Q to the N in here, and let's see. Then 1 phi 0 Q to the N, nothing, QZ. This is just the theorem. The theorem says infinity. But do you think you can simplify this? They have many things in common. Infinitely many things. Because this thing, it begins with 1 minus z, and then 1 minus z q, 1 minus z q squared, dot, 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 dot. And at some point, after nth factor, it will be the same as this. You can kind of cancel this and end up getting z q sub n over 1. All right? This cancels. And what is this? Let's write this using a more familiar term. I'm just rewriting this. This thing is equal to here. Summation n from, let's use I from 0. This thing is q to the n qi qi z to the I. Z raised to I. Okay? Just this thing. And what is this? You can see this is just n plus I minus 1 I q binomial coefficient. Okay? Here, if you remember, nk, it is by definition but this is equal to QQN, QQK, QQN minus K. Because n, this n, Q integer is 1 minus Q to the N. Q factorial is Q, N, 1 minus Q to the N. If you use this, 1 minus q power of 1 minus q, they are the same in the numerator, denominator, they cancel that, so we get that. So this is, you will use this often. So here, this just becomes this. So in this case, so corollary, we just proved that ZQN equals I from 0. This is more familiar than the the previous Q binomial theorem. This is a Q analog of what? So 1 minus z to the minus n equals. This is one form of the binomial theorem, right? If you remember, this is nothing but minus n choose I. So, and if, by the same idea, if you consider A equals Q to the minus n, then you get this corollary. The same idea, you just simplify this or change this in a familiar term, then you get this. This is a Q analog of this, or minus z n, or okay, let's plug in z equals z, so that we don't have minus there. Then it's going to be z to the I, like that. Okay, this is Q analog of this. Right? If Q approaches 1, this becomes this, and this becomes this. So this, both this and this, follows from the Q binomial theorem. And that's the reason why we call that Q binomial theorem. Any question? Do you think it's complicated? Yes, it looks complicated if this is your first time. Yeah, I felt the same thing. It looks very complicated and looks scary, but there's nothing very serious here if you know the notation and if you know what's going on. They are just long, not hard. So you just need to practice by solving some problems, homework problems. You will hopefully get familiar with this and be comfortable with this. And you will understand that, you will see that this is very powerful and useful. But because this is very long, it's very likely to make mistakes if you do this. So for me also, when I use hypergeometric series and try to prove something, I almost always make mistakes. So I have to correct this after doing this. There is always a power of Q off by something, so I need to fix this. But at the end, I get the identity correct, and I can prove something. In my research, I really use this very often, and I find it very useful. So I hope you also appreciate the usefulness of this. Because if you know this, there are many things that you can prove. It will be a very useful tool for you as far as identities are concerned. Okay, and also a corollary, we have this limit Q approaches 1. You can write Q raised to A proof. We know 1F0. This actually follows from the Q binomial theorem. Because we can obtain hypergeometric series always from a basic hypergeometric series. You know, we don't really need that. Okay, we know this. This is a consequence of the Q binomial theorem. So left-hand side here is this is Q binomial theorem. And this, we know from the proposition, changing this into this is 1F0. And of course, this is 1 minus Z today. So that we can consider the limit of this ratio of infinite products. And actually, there's a better way. Okay. But of course, another proof for short proof is this is nothing but Z Q raised to A to 1 if A is an integer. If A is an integer. Here it doesn't necessarily an integer. It doesn't have to be necessarily an integer. If A is an integer, we immediately see that this is 1 minus Z. But for general A, we also have this. So there are many consequences of Q binomial theorem. We already saw 2. And another one. So one phi 0 is always expressible as a product. What about 2 phi 1? 2 phi 1, not always. But there is a transformation called Heinz transformation. Two phi 1 A B C Q Z. This is equal to B A Z Q infinity C Z Q infinity 2 phi 1 C over B. It's not a summation formula. So usually summation formula means something, sum equals just one thing. But this is sum equals sum. So it changes 2 phi 1 as a different 2 phi 1. So maybe you don't have a summation formula for this in your list, but maybe this may have. So it may be useful to change this into a different one. Okay. This can be proved using Q binomial theorem. Not sure if I have enough time to do this, but proof using Q binomial theorem. Yeah. I'm going to just say that, see the lecture note. Not very long, but yeah. If you have time, we will do this, but yeah, because I try to finish today's lecture at before 11, so let's just leave this as a reading assignment for you. And there is another version of this. Okay. Again, it's Heinz transformation. We apply this again and again. Then there are several different ways to do this. Then we get 2 phi 1. I'm just repeating the same thing. This is the same thing. I'm just rewriting this. And you apply the same thing over here, then you get C over B. There's a different form. And also, if you do this one more time, then you get this. So if you want to change 2 phi 1 in a different 2 phi 1, you can try to use one of these 3 things. They are all called So, I omit the proof of this. Yeah, I said I don't have enough time, but proof, it is more important than, applications is more important than proof here, I would say. Because this is true, all you need to do is to apply this. You don't really need to prove this. Because, application is more important. Also, for here. In the third one here, if you replace A, B, C by Q to the A, Q to the B, Q to the C over here, and if you let Q approach to 1, then you get this. This is called Euler's transformation. This is called Euler's transformation. So they all give each of these gives a hypergeometric series transformation. Q, like I said, Q hypergeometric series is a generalization. Okay, now you will see some consequences of this transformation. So when some of these are special, then we get really a summation formula. Okay, so some consequences. We let Z equals C over AB in a Heinz transformation, then we get things like this. A, B, C, I'm just plugging in two phi 1. Then it turns out like that. I just used this thing, Z equals C over AB. So you replace this by C over AB, this by C over AB, then you get this. What's nice about this is that you have the same thing here and here. But if you have the same thing, you can cancel this because they represent the same factor. And then you can reduce this by 1 and 1. So this part becomes 1 phi 0, right? But 1 phi 0 is always summable. So it's always a product. By the Q, here you use Q binomial theorem. If you apply Q binomial theorem, then you get B C over B Q infinity, C over AB Q infinity. We have one thing here, so it's going to be this times this. So C over A times infinity and then B infinity. Oh, by the way, sometimes people omit this Q when it is clear. Sometimes, because it takes a lot of time to write this all the time, simply like that. Yeah, I'm kind of abusing the notation because this is rising factorial, but if it's clear that we are doing Q, then sometimes I'm going to just use like that. Or not, let's not do that because this is first time I'm going to use Q always there. Okay? So what now? We can cancel this and this. So corollary, 2 phi 1 A, B, C, Q, C over A, B. This is a product. Here, C over A, C over B, Q infinity, C over A, B, Q infinity. So this Z, if Z is equal to this over this times this, then we can write that as a product. And moreover, if Q equals, if one of these is a power of, negative power of Q, then we get even better. Then what happens here? This is, this part is CQN, C over B, C, what is this? Q to the N, C over B, Q infinity. Now what? You can cancel this, right? So this part you can cancel this, you get C, Q, N. If you cancel this, and if you also cancel this, you get C, B, Q, N. All right? So this is called Q Vandermon's formula. So here N is a positive integer. So if you have Q minus N, B, C, so I just replaced A by Q to the minus N. And here this becomes C, Q, N over B. This is equal to C over B, Q, N, C, Q, N. And this is equivalent to this. Oh yeah, I need more space. Okay, so equivalent version. Proof of the equivalence is also in the lecture note, so if you want to see the proof, you can see the lecture note. So here in the previous page, this is special, like determined by these three things. But if this is just Q, then this is also expressible as a product. This is basically equivalent to the Vandermonde identity. So this is also called Q Vandermonde identity. They are equivalent. And here, if B replaced by Q to the B, C replaced by Q to the C, and the Q approaches 1, then we get 2F1 minus N B C 1. This is C minus B N C N. This is called Vandermonde's formula. Okay. So the proof of the idea of the proof of this to show that they are equivalent, you just change Q to Q inverse and then try to simplify things, then you will obtain this. They are basically equivalent in that way. But for the details, please read the lecture notes. Okay, so now I'm going to tell you why this is called the Q Vandermonde identity. Because this is a generalization of the following identity. Let me write that down. So the corollary. This is a Q Vandermonde identity. Right? So the Vandermonde identity is like the binomial coefficient without this. But Q approaches 1, this becomes the usual Vandermonde identity. So let's prove this using the Q Vandermonde hypergeometry, the basic hypergeometry. So again, an identity like this can be proved by the same steps. First, express this as a basic hypergeometric series, and try to see if you can use any identity, known identity, and that will finish the proof. Okay, so first step, we need to express this as a cube hypergeometric series. All right, what is the left-hand side? Q. All right, so this QM K minus I, QI, and here QN I N minus I. Oh, I already made a mistake here. This is not I. M minus K plus I. Now you express each vector as a Q Parker-Hammer symbol. That's what you need to do. So what's this? This thing is good. Q M minus K plus I. What is that? First we have M minus K term, vector. M minus K, right? And then after that, we get 1 minus Q to M minus K plus 1, and then N minus K plus 2, etc. So it's going to be Q to the M minus K plus 1, QI. Okay? So this is good. This is constant. This is perfectly good Q Parker-Hammer. And what about this? QK minus I. First, try to consider all K factors like this. They're like K factorial. 1 minus Q squared, 1 minus Q to the K. But we have more factors here, so we have to divide this by what? Okay, let's write this down. So the last I factors are not here. So we have to divide that by 1. But we can have this, Q inverse Ki. Right? Because this now is like decrease the power exponent of Q by 1 at a time. Okay? But there is a way to change this as the usual Q Parker-Hammer symbol. Let's see. Okay, what is this? In general, if you have something like this, I, you can write this as a base Q, because we want everything base Q. So what is this? Just try to do this step by step. Minus I plus 1. Okay? Factor everything outside. I mean, first factor minus 1, so minus 1 to the I. Move this outside, move this outside. So it's like AQ inverse AQ minus I plus 1, like that. And then after that, because we factored A out, we have 1 minus A inverse here. Here, this becomes 1. Now, the inverse of this, 1 minus A inverse Q, it's like that. Minus. Okay? So this is what? We have I, so minus A raised to I. This is Q to the sum of 1 minus 1 plus 2 plus dot 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 I, so it's I choose 2, minus I choose 2. And then this part is minus A Q I. So you can change this like that. You just need to, you can just remember this thing, and then this part is what? Minus A, so minus Q to the K raised to I, Q to the minus I choose 2, minus Q to the K, QI. Just like that. All right? So this is done. This part is done. This part is done. This is basically the same as this. So you can, everything is now okay. So we are ready to write that down. So yeah, we just need more space. That's the problem usually. Okay, let's see if I can do this. So left hand side. Here, I is from 0. This thing, QM. This part is now this. Let's write this as minus 1 to K, Q to the KI, minus I choose 2, minus Q, K, QI. This is done. Now this is this. Q, Q, M minus K times in the denominator. Okay. Let's do this. I, this, like that, times this. Q, Q, I. And this part is the same as this, only we have, oh, yeah, I made a mistake. This is I minus 1 to I. Everything here the same, except we have N instead of K. I choose 2, N, Q, I. That's it, right? 분자에. 어디요? 어디 또 이상한 거 있나요? 저는 항상 like I said, I always make mistake. That's the problem. 어디가 이상해요? 어떤 게? 잠깐만, 요거 이렇게 됐지. 요거 됐지. 요거 됐지. 아, 이거? 아, 그죠. 아, 네, 맞습니다. 아, 많이 빼먹었네요. Okay, so I made a mistake, but we can fix this, as you already pointed this out. Up to some correction. Okay, let's do this again in the next page. Okay, I'm going to just simply yeah, it should be in the top. I choose. Yeah, it should be in the numerator. And we have this. I also missed this part, right? And Q n minus K, Q n minus K plus 1, Q I, and Q n minus 1, I, Q n minus n I, and choose I choose 2, minus n Q I, quite complicated, but nothing like clever at all. Now some cancellation. This is the fun part. You cancel many things. Minus 1, and try to factor things that are constant. So this is constant. So this is going to be, this is exactly m choose k, like that. Okay, now let's consider this power of q. Okay, what is the power? Here we have I squared, right? So if you consider this, you will see this is equal to this. It's like that. If you combine these three things together, you will get this. Oh, this is 1, sorry. Okay? Plus 1. And Q minus K, Q I, Q minus n, Q I, Q I, and then this. Oh, plus n minus k plus 1, Q I, and that's it. So this is z. So this z is q to the n plus 1. So this is what? This is q hypergeometric series 2 phi 1. We have this q to the minus n minus k m. Oh, this is m minus k plus 1 q to the here m plus n plus 1. If you see, this is equal to this divided by this and this. Do you see that? This divided by this and this. If this is A, B, and C, and this is, you can see, C over AB. Oh, or this is, let's just leave there. This is Q, C, Q to the N over B. Okay? So it is a product. So here we use the Q Vandermonde. N plus 1. Now, if you simplify this by expressing this as a product of Q Parkheimer symbols and then try to cancel everything, you get this. That's the proof. Yeah, a little lengthy, but yeah, the same idea. Any question? So from the using Q binomial theorem, we obtained the Heinz transformation, and as a special case of Heinz transformation, we have Q Vandermonde. Q Vandermonde proves really the Vandermonde identity, Q version of the Vandermonde identity like this. And there is another application of Heinz transformation. So here, the general form of the Heinz transformation. This is one of the Heinz transformation, A, B, Z over C. But something infinity over something infinity. This is Q binomial in the one side of the Q binomial theorem. So this is equal to what? 1 phi 0 A, B over C, nothing QZ, right? Which is summation n A, B over C, Qn, Qn, Z to the n. Okay? So here we have one summation, or here summation n A, B, Qn, QC, Qn, Zn. On the other side, we have product of two series, A, B over C, Q, N, Z, N, for this vector. And for this, I just rewrite this, C over A, C over B, Q, C, Q, N, and A, B, Z over C to the N, right? So we have, this is equivalent to this, they are the same. But here we can deduce another identity because you can write this as a single sum, right? If you collect Z to the N, then you get some kind of sum, I from 0 to N, and then this ith coefficient, N minus ith coefficient, like that. I'm not going to write that down. So here, if you compare if two series are the same, their coefficients must be the same. So we have an identity like summation equals product. If you and this turns out to be another hypergeometric series, 3 phi 2, that becomes a theorem like this. This is 3 phi 2 identity. It's called Q Salsutz summation formula. So 3 phi 2 is an example of a 3 phi 2 that can be summed. So 3 phi 2 not always, I mean, oh yeah, it turns out to be a 3 phi 2 sum which has this thing. Oh, by the way, this is a series, infinite series. But if one of these is a negative power of Q, then it is a finite sum. Do you see that? If you have this, if I is bigger than A, N, then it's going to be 0. Because at some point, if you have enough many factors, then you have Q to the 0, which is 0. 1 minus 1 is 0. So if you have this kind of thing we say is finite sum. Whenever you have this term, it's finite. That, like here is finite sum, not an infinite series. A, B, C, inverse Q, 1 minus N, Q, Q equals C over A, C over B, okay, so here you can remember this as follows. So here must be QQ. What is this? They look complicated, but what is the product of these two? Product of these two is A, B, Q, 1 minus N, right? Product of these three are A, B, Q minus N. They are off by Q, right? So if you have, so the product of these is equal to the product of these times Q, then we can, and if the Z is Q, then we can write this as a product. That's basically that thing, okay? So sometimes if you have 3 feet 2, and if that's of this form, then you can rewrite this as a product. And a theorem, so this is just Sawtooth summation. This is obtained from this. Summation formula. 3F2 minus N, let's write A, B minus N, C 1 plus A plus B plus C minus N 1. Again here the sum of this is the sum of these plus 1. C minus A N, C minus B N, so that's it. So the identities that I told you today, like Q binomial, Vandermonde. So Q binomial is for 1 phi 0, Vandermonde 2 phi 1, so Q Sawtooth 3 phi 2. So these are the simplest identities in hypergeometry. There are more and more identities, but they are quite complicated. There is a summation formula for 4 phi 3 and even like 6 phi 5 and things like that. They get more and more complicated, but the idea is quite the same. So if you practice this, you can use this, and you will prove identities like very easily. Any question? Do you like this? Do you think? Yeah, I think some of you may like this, or some don't. But I would say it's very useful. So if you are willing to learn this, it will be very useful for you. Okay, so today I'm going to finish right now. Thank you for your attention.